Okay, so on Friday, you were supposed to be using your rules in order to solve problems, but I think it's a really worthwhile activity to just simply see how these basic results, not the basic results, all the rules are derived. There's only 3 of them, plus there's 2 basic results. So the basic results are these ones here. If I have a to the power of 0, then that's equal to, hey, so therefore log base a of 1 is equal to 0. Okay? If I have a to the power of 1, that's equal to a. Okay? So that means that log base a of a is equal to 1. 2 basic results. They're fundamental results because they come from the fundamental definition of what a log is. Okay? Of what a logarithm is. I'll zoom out now so we can keep that on the screen. And let's now have a look at the 3 fundamental rules. Shall I look at 3? Yeah, I won't use the 4th one. So there's a 4th one as well. And by the way, excuse me, I'm sorry for clearing my throat. These are all results, not the 2 basic results, but the 3 rules I'm talking about are on your theory sheet. Sorry, your information booklet. This is condensed into one sheet, but you'll get a full booklet. And you'll see in the topic 1, number and algebra, it says, excuse me, I'm so sorry, exponents and logarithms, and there's a bunch of things there. But it's actually there's basically 4 rules or 3 rules and a theorem. Sounds like a really bad TV sitcom. 3 rules and a theorem. And we're going to have a look at the 3 rules today. Because they're kind of tidy. So I'm going to lead you through the first one. They are covered in your textbooks, but I think it's better to see it. I'm going to do the first one. I'm going to get you to do the second one. So let's set up. Okay, well, let's state the rule first. The rule number 1 is that log to a base of x, y. Now, when I've got things multiplied together or added together that I'm applying the log to, I put brackets around it to say that whole thing is applied to the log. If it's just one thing, you can get away without brackets, even though it's a function. We know that normally with a function, we put brackets around it, like f of x. This is log of xy. But because logarithms are so common, it's the same thing with sine and cos and tan as well. It's common practice not to use brackets. But just remember, this never means log a times x. Never. It means apply x to the log base a function. Anyway, the rule is that log base a xy is log base a x plus log base a y. That's the rule. Okay, so let's have a look at that rule in action. This is kind of like the proof of the rule. So we're going to let x equal a to the power of m, and we're going to let y equal a to the power of n. Then what does xy equal in terms of a, m, and n? And remember, when I say in terms of, it means the result is going to include those things. So x is a to the power of m, y is a to the power of n, and so therefore xy is excellent. Okay, so we multiply based upon our index laws, our exponent laws. If I multiply 2 things together with the same base, I add the exponents together. Say that again. When I multiply 2 numbers together with the same base, I add the exponents. Okay, let's translate all 3 of these 3 things into log. So just by basic definition. Also, therefore, log base A x equals m, log base A y equals n, log base A xy equals m plus n. Just by basic, this line here is using our basic definition of a logarithm. The base becomes the log base, the power becomes the, in inverted commas, the answer, the result, and the argument, the thing I'm putting into the logarithm, is this bit here. So I've done that goes to there, that goes to there. This is a more complicated expression, but still the same thing. Goes to there, that goes there, that goes there. This is the new power, and so that goes there. Any questions? Oh, right, you guys are going to be easy then. So taking this result here, therefore, log base A xy, what does m equal? Log base ax. What does n equal? Log base ay. And thus it is proven. It's not really a proof, but I'll put QED because it looks fancy. Now if it helps, you might want to color code it. So you've got this, this, and this. And then you've got this, and this, and this, if it helps to color code. Is that easy enough? Wow, great. I'm so pleased you found that easy, because now I'm just, since you said it was easy, because no one said, no, actually, Richard, that's actually quite tricky, and what are you talking about? Since that is so easy, so now use a similar logic to prove rule number 2. And rule number 2 is that log base A of x divided by y equals log base A x minus log base A y. Prove that sucker. So there you go. Of course, you're stuffed if you don't know your log rules. I mean, your power rules, of course. But the critical one here is that when I divide two numbers with the same base, then I subtract the exponents. Okay, so a to the power of m minus n. By the way, one student asked me whether they could prove it by looking at a specific example. The problem with looking at a specific example is though you can prove it. So for example, log of 8 divided by 4, log base 2 of 8 divided by 4 is the same as the log of 8 minus the log of 4. You can do that, but it just proves that it works for that example, you know? So it means that for log base 2 of 8, you know that's 3, and log base 2 of 4 is equal to 2. 3 minus 2 equals 1. And so you can do all that, but it just proves it for that particular set of numbers. The power of mathematics is to generalize. We talked about this at the start of the year. It's finding patterns. And algebra is just the formalization of patterns into rules. But patterns apply generally. Whereas if you're looking at specific numbers, then you're just looking at a specific result. There's a few things that I should do, which I haven't for simplicity's sake, like say that A has to be a positive number, for example, greater than 0, etc. Those kinds of things. I haven't really specified the restrictions on A and X and Y like I should have. But nevertheless, I think we can take it as understood in a logarithm unit what A and X and Y could be, just for the sake of simplicity. Okay, I'm going to get you to try and do this third result, and I'm going to give you zilcho guidance to start with. Maybe I'll give people a hint individually. You now have, with everything I've gone through on the board right now, believe it or not, you have the power to work out rule 3. Do not use your textbook. Rule 3 is if I take a logarithm base a to a value x raised to the power of m, I'm using the same letters and by the way as your formal rule sheet uses, log base a of x to the power of m is equal to m multiplied by log base a of x. So the way I say this is that I can take down the power. The power is taken down in front. That's the rule. And you've got, I've already said before, you've got the capacity, as in the tools in front of you, to work that out. You just need to think about what x to the power of m means. Maybe start by using a specific example like x squared to see if you can figure out how you would work that out, and the rules that you've already got. I'll say no more. I'm going to pause this recording. I'll give more hints to those that are absolutely flummoxed, but try and persevere to start with. Look at the rules you've got so far. How could you apply them? Which ones are applicable that you could apply to working this out? So a lot of you are getting there, but it's just a matter of putting it together with a little bit more. It's simple communication. It's half of mathematics battle is trying to express something in general and in general terms instead of specifics, and the other half of the maths battle is to know how to write it without being too wordy. I might just zoom up on that so you can sort of see it a bit more. First of all, just to illustrate, if I just do, I'll erase this, so I'm not keeping it here. If I do log base ax squared, then that's log base a x times x. And rule 1 says that if I have two things multiplied together, then that would be the first thing, the log of the first thing added to the log of the second thing. Now, if I've got the first thing added, if I've got two things here, then this is just a number, right? I don't know what the number is, but it's a number, and I've got two of them. And so that's equal to 2 log base a x. Okay? So that's how to do it for the square. If I did a cube, then I'm just going to have log xxx like that, triple x. And I think it's is it a fairly simple jump to say that would be the three things added together? Even though the rule doesn't directly give me what happens when I've got three things instead of two things, I hope you can see that if I wanted to, I don't want to, I could just treat xx as a unit. So I could say that's log base axx plus log base ax, and then I can just add 2 log base ax and log, etc. So I hope it kind of makes sense that this would be log base ax plus log base ax plus log base ax. Oops, sorry about my messy writing there. Which would give me 3 log base ax. So I hope that makes sense from that perspective. But again, all we've done is we've shown it for a square and a 3. We want to work it out in general. And it's just like I said, it's just a how do you write that efficiently once you've got the idea? So I'll go log base ax to the power of m. And instead of writing it, well, then I go x times x times x dot 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 x like so. And then I just use a sideways curly bracket and say I'm doing this n times. And at this point, Libby said to me, well, that doesn't look very mathematical. And it's not full of magical symbols, I know, but does it articulate what I'm doing? Yeah, it does. You can see from that I'm multiplying x by itself m times. And so then I can say my next line is log base ax plus log base ax plus dot 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 all the way to log base ax, and I've done that m times as well. like so. Now, if you're really keen, I wouldn't do it, but you could probably just go. You could do that. That would give you the same. Lily, that's for you because you said you wanted it more mathematical. So you could use your sigma notation to say, I'm adding log base AX m times. That's what that means. Again, only Lily's allowed to do that. The rest of us will use common sense. Okay, so and since I'm adding the same thing together m times, I get m log base AX. So it's quite a lovely little result, isn't it, really? When you might think, well, in the last however long that took us to think about that, 15, 20 minutes, is time we could have just been used practicing the rules. But I think there's something really, to get to that point, the mathematical thinking you have to do to get to that point, to realize that log base A is just a number, that I'm repeatedly adding a number, even to the extent of thinking about that there is definitely a link between raising a number to the power and the fact that it's a repeated addition as well. All of these things are really good mathematical concepts to follow through with. Yeah, so there you go. There are the 3 rules. Now, I'm going to ask a question. Your work on Friday was to complete exercise 9I from 9H from memory. That's not a question yet, is it, though? Who finished 9H? Who's nearly finished 9H? Like, you got a little bit to do. Okay, what am I trying to say? I'd like to say complete 9H by Thursday. If that's a killer for anyone because it's like that's a massive amount of work, or because you won't have time or whatever else, can you speak to me one-on-one? But other than that, I'm going to assume that 9H will be completed. The basic understandings of applying those rules, I think. And then on Thursday, I'm going to get us stuck into 9I. Plus, we're going to have a look at natural logarithms. And to look at natural logarithms, we have to understand more about what E is, or Euler's number. And we've got about 12 minutes left of this lesson. I've got about a 10-minute video that I'd like to share with you because I think it would be worth it. Because understanding, basically, this maths course could be done like this. E is about 2.7. Okay, now let's use it. But I'd much rather take you along the journey of where does this number come from? Why is it so special? So special that it's named after one of the most famous and brilliant mathematicians of our time, Leonard Euler. It's really worth sort of seeing that in action. And we get to start to see, so we're going to have a look at E. So we're going to go back to base to the power of notation, while in this video, E to the power of as a very important very important value. And then we'll tie that back into logarithm work on Thursday. So I'll just stop this video now and do exercise 9, was it H? By Thursday.